So today we're talking about strengths of acids and bases, and then you'll notice underneath here it says percent ionization. And again, that's another percentage. We've encountered percentage multiple times in chemistry. It's a very easy way to express to a certain extent that how far a particular process goes. We've talked about percent yield, how far the reaction goes in terms of being complete. In terms of percent ionization, how far the ionization process goes, expressed as a percentage. We're going to start by talking about strengths of bases, just because they're a little simpler to discuss than acids. They're not nearly as complex of a calculation. So according to Arrhenius and from our Bronsted-Lowry theory, if you can get a lot of OH as a product in the water, you've got a base. In terms of our knowledge of concentrations, if you can get a very high molar concentration of OH, that means a large number of moles of OH per liter, then you have what we would consider a strong base. So now strengths of acids and bases can be quantified by calculating how much of the hydroxide ended up in the water. Now, in order to do that, we're going to look at ionic bases, and I'll bring up the factors that affect how many OHs end up in the water. So really the question becomes, how can we get as many OHs into a solution as possible in order to make it strong? And the three factors that affect this, number one, the number of OHs in the compound. If I have something like sodium hydroxide, it only has one OH, right? NaOH, we do the crossover, NaOH, and we'll write these examples down. There's only one OH. When you dissolve it, one OH falls off, ends up in solution, floating around there, surrounded by waters. And so you only get one OH per NaOH. But if I were to dissolve it in something like barium hydroxide, if I were to dissolve barium hydroxide in water, then I would have two OHs fall off for every single barium hydroxide. If I had the same number of moles of sodium hydroxide and barium hydroxide that I dissolved in water, the barium hydroxide would actually be twice as strong because I'd end up with twice as much OH in the water. So the number of hydroxides that are able to be released in the water per ionic entity determines the strength. A second factor, this one's an obvious one, the concentration. It depends on how much of that particular solute I put in the solution. If I put in only a gram of sodium hydroxide versus 30 grams of sodium hydroxide, I'm going to get a lot more hydroxide in the water if I dissolve more. The concentration. The more concentrated it is, the more hydroxides are going to end up in the water. And the last factor is a subtle one, and I'm not going to make you do any calculations with this, but it is a valid one, and it's the solubility. It's whether the substance dissolves well or not. We can check on our solubility chart the hydroxide line, and we can take a look that Some of the hydroxides are very soluble. They're aqueous. And then there's some hydroxides that are less soluble. They form a solid. And if it doesn't dissolve, if they're a solid, when we dump it into water, then they're not going to release very many hydroxides to the water because they're going to be stuck in the solid. The solid will settle to the bottom. There will be no hydroxides released, or very few anyway, and there will be a weak situation. There won't be a lot of hydroxide in the water. Let's write examples of each of these. Here's the first. I just wanted to put the first one up, but I'm not. There we go. We'll back it up. So in the first one, you can see here that we've got NaOH. It falls apart. We end up with one OH for each NaOH. And you end up with a 1-to-1 ratio. Again, the more concentrated I make it, the more OHs I'll get. But for each single NaOH, you get one OH in the water. The second example was our barium hydroxide. When it dissolves, two OHs are released. So if I had the same concentration of barium hydroxide as I did sodium hydroxide, this would actually be twice as strong. I'd have twice the OHs in it. And to illustrate the last one, the solubility, if you take a look at something like magnesium hydroxide, magnesium hydroxide actually has a low solubility. It doesn't dissolve very well. We may have mentioned magnesium hydroxide when we talked about bases. Actually, it might have been the morning class. Magnesium hydroxide, did we talk about antacids? Did we talk about antacids? We talked about magnesium hydroxide, milk of magnesia. You can go into a grocery store, get some milk of magnesia. Got an upset stomach, you take some of that. It neutralizes some of the stomach acid. Magnesium hydroxide is what's found in milk of magnesia, and that's because it doesn't dissolve very well. It probably says on the container you got to give it a shake because all of the solid will have settled to the bottom, and when you shake it up, you give it a big mix. It's a white powder, so when you pour it into a container, it looks like milk. But it's made up of solid little pieces of magnesium hydroxide that don't dissolve. Only a few OHs are able to get into the water. A very small amount of it dissolves. So when you take a drink of it, it probably tastes a little bit bitter, but it's not dangerous because there's only a little bit of OH in the water. It's not going to burn your esophagus as you swallow it down. You could probably use sodium hydroxide as an antacid. It would neutralize the acid, but because in sodium hydroxide all of the OHs are already released, when you take a drink of it, those OHs are going to react with the walls of your esophagus, and you'd end up with some kind of, I don't know, very painful affliction of a burnt esophagus from the base as you swallow it down. I'm sure that would be very painful and dangerous. So you wouldn't want to do that. You wouldn't have an upset stomach, though, anymore. Anyway, you'd have other bigger problems. The reason magnesium hydroxide still works as an antacid, once it gets into your stomach and it's surrounded by the hydrochloric acid, what can happen is the hydronium ions, the acid particles, right, the H plus or the H3O plus in your stomach, will go and will act on that and dissolve it. As it dissolves it, it releases the OH and it's neutralized right away. So the acid starts to dissolve it and then it's neutralized because it releases the OHs. So it releases the OHs down in your stomach in an acid situation where it's not going to be dangerous because it's going to be neutralizing the acid. All right. Now, I've got an example on a little worksheet a little later on that involves magnesium hydroxide. That's because I don't have a whole lot of options with atoms that are going to have two OHs stuck to them. I'm going to ask you to treat it as if it dissolves completely. I'll mention that a little bit further on. I just needed another example other than barium hydroxide to give you. All right, so that's how we deal with ionic hydroxides. Does it dissolve well? How many OHs does it have? Okay? Let's now talk a little bit about covalent bases, molecular bases. And actually, we're going to be talking about molecules from here on in because all of our acids are molecular. So now we're going to be talking again about our Bronsted-Lowry theory. We're going to talk about this idea of a game that I kind of expressed to you, how you can think of this acid-base Bronsted-Lowry theory as some kind of a keep-away game concerning H pluses, transferring something, giving up an H plus, or maybe having it taken away, something else acquiring an H plus. And in yesterday's lesson, we just talked about the transfer of the H plus. In today's lesson, we need to look a little closer, not just at the transfer itself, but at the ability of the molecule to do the transfer. How good is it at that particular function? So if we extend this idea to our little game, the question we're asking now is, how good is the acid or base at playing the game? Is it, prolific? Is it that kid in gym that wins everything and dominates everything? Are they excellent at playing it? You end up in partners playing whatever sport, and you end up against that kid, that athlete kid. There was a Disney show called Recess with a kid that had a hat he wore all the time. What was his name? TJ. And then there was the athlete kid, Vince. Was it Vince? Vince. Vince would be great at this game. He would be the kid who would dominate this game. He would be phenomenal at it. Now, just a reminder, what's the game? Well, when it comes to a base, well, you tell me, a little bit of a reminder. In terms of our base, what does it do with the proton? A base does this with the proton. Yep. It's an acceptor. It's an acceptor of the proton. All right? So let's write that down just as a little bit of a reminder. This is the base. Acceptor. Base. In this case, the water is the acid. And let's complete it. After the base has accepted, what does it become? What does the base become after it's done the accepting? Yep. Yeah, the conjugate acid. And OH, conjugate base. Conjugate base. And when it comes to bases, the name of the game is accepting. The name of the game is taking the proton. So NH3. How good is NH3 at taking the proton? So like I said, if the base is a good base, a strong base, you've got Vince as NH3. Put him in the water, what does it do? Takes away the OH, takes away the H from the water, turns it into OH. Its competitor is this, OH minus. What's it going to do? It's going to try to sneak up on an NH4 and take it back, turn it back into NH3. This game goes on and on. One trying to take it from the other trying to take it back. The question is, how good is the NH3 at playing the game? If the NH3 is really good at playing the game, and it takes the H's from as many as it can, for every mole of NH3, it takes away pretty well a mole of H's, then we're going to get a mole of OH minus. That's a strong base. But if it's not very good at the game, let's say the OH is better, sneaks up on it, takes the H back, that means all of this OH that was formed is going to be turned back into this, and we're not going to have very much OH existing because it's taken the H back. Then if it loses against the OH and it pushes it back this way, then we have a weak base because not very many OHs will be formed. So when it deals with the molecular base, the question is, how good is this thing at taking the H's? That's how you determine whether it's strong or weak. Question? At this point, you don't. But next year, I supply you with, not that table. They're going to make me find the table. I can't find it right now. I got it in here somewhere. I'm going to give up soon. Doesn't matter. Next year, I supply you with a table that has all of the bases, and it supplies you with a number that tells you how good it is at playing the game. It's that simple. And that's the only way we can do it. It's not that the number's been assigned to it. It's that chemists have done measurements to determine how much OH is formed. And then from those measurements, they can do a calculation to say, all right, this base is, yeah, it's not that great at playing the game. I don't get very many OHs. We'll assign it this value. It's actually a mathematically calculated value. And that then determines how strong it is. It turns out that NH3 is not very good at this game. It's kind of a medium guy. It's not like it's super weak, but it's not strong. It's what I would call moderately weak. All right? You will learn next year how to deal with those numbers. Right now, I'm just introducing you to the concepts. So I will not have you do any calculations on covalent bases. Okay? All right. Let's now talk about the acids. Same thing for the acids, except now we're talking about H3O pluses. How good is the substance at producing H3O pluses? So again, a strong acid is something that has a lot of H3O plus. Again, to link it to the last couple of days, the Arrhenius theory really is only concerned about the H3O plus. The Bronsted-Lowry theory explains where the H3O pluses come from. They come from the trade of the H. So the more hydronium ions per liter, the more moles per liter, the stronger the H3O plus, the stronger the acid, the more dangerous the acid is. Now, we don't have any examples of ionic acids. They're all molecular. You put them in the water, you set them off on the game, you let them give their H's away, and the question then is asked, how good is that thing at giving up its H's? Again, it's like this game, except for acids, it's not wanting to get an H. For acids, it's giving up its H. So the game goes from being a keep-away game to more like a hot potato game. Get rid of the H. You want to get rid of that H as quickly as you can if you want to be good at being an acid. Let's take a look at a couple of examples here. Yeah, let's not worry about this. We're just gonna move on. This is not a big deal. Due to the fact that all acids are covalent and most of them are solid, the strength of the acid depends on how well it can give up its H's or how well it can ionize. I will give you two examples of that right now, so no need to write that down. So I've brought two examples up. One that represents a strong on the left, one that represents a weak on the right. In terms of our game, HCl on the left is great at it. It gives up that H very easily. In terms of the weak one on the right, this is acetic acid. It's not very good at it. It doesn't give up its H's very easily. Again, keep in mind, this is all happening in water. We've seen acetic acid, CH3COOH. It's the last H is the one that falls off on that particular version of writing the molecule. So hydrogen chloride, put it in water, hydrochloric acid. Almost 100% of it ionizes. It's not exactly 100%. It's in the high 90s. There is a little bit that is formed back the other way. But again, in terms of our game, here we've got our H+. It gives it to the H2O, makes it become an H3O+. The reverse situation is if the H3O+ gives it back to the Cl and brings it back, turns it back into an HCl. But in this case, because it is strong, almost 100% of it is turned into the Cl- and the H3O+. This type of reaction that can go both ways, and we will learn more about it next year, is called an equilibrium reaction. And in an equilibrium reaction, we have the forward reaction happening, and at the same time, the reverse reaction happens. And the question is, which one happens faster and which one happens to a greater extent? In this case, the forward reaction happens to a much greater extent than the reverse reaction. And we can represent that with a double-headed arrow. I'll put an arrow here up above. It's a lot larger than my one that I'm going to put down below. That goes back the other way. So there's my arrow heading back the other way. And that's what we would call an equilibrium arrow. We actually wouldn't use that regular arrow. But in this case, it means that the forward reaction happens a lot more than the reverse reaction. It happens a lot quicker. And therefore, we have a large amount of H3O+ that's formed. In the acetic acid, in this case, we're saying only 1.3% of each of these CH3COOH molecules proceeds and successfully gives up its H. So if I were to represent this arrow here as an equilibrium arrow, the forward arrow would be really tiny, and the reverse arrow would be really big. That means that this reaction actually produces very little product. Acetic acid is very poor at giving up its H's. Only 1.3% of these guys give up their H's. That's a good thing, I suppose. You put some vinegar on your French fries, you eat the vinegar, you taste that tartness, but it's not so strong that it burns your esophagus again as you swallow it down. And that's because only a few of the H's fall off, all right? A very small amount. You wouldn't want to put hydrochloric acid on your fries. It would be just bad, just like taking the sodium hydroxide. You don't want to take the strong ones. Weak ones, your body can handle. Okay, so how are we going to determine mathematically the exact amount of H3O+ or the exact amount of OH-? And we're going to do calculations that involve what we call percent ionization. So another percentage equation to learn. But again, every percentage equation is the same. How much did what we were expecting to do, how much over what the total is, times 100. It's always that. Percent yield. You know, how much did the experiment actually yield? All right, divided by what you expected it to yield if it was perfect, times 100. Right? You want to determine the percentage on your test. What did you actually get on the test over what you would have did if you got it perfectly correct, times 100? What's the percent ionization? Take the concentration of the H3O+, which is the amount of it that successfully reacted, actually, divide it by the total concentration of the acid, which is what you could have had if it were to all ionize, times 100. It's a percentage of how much of the reaction successfully goes to the other side. And for every molecule that successfully gives up its H, we get one molecule of H3O+. It's an ion, essentially. And so this is a measure, the H3O+ is a measure of successful reactions. And that's what we want to figure out, because pH is going to be able to then tell us that value as well. That H3O+ is related to the pH. Just a couple of conventions here that scientists have assigned these numbers. If an acid is got a percent ionization of greater than 99%, we say that it's strong. Pretty well, all of the H's fall off. If an acid has a percent ionization of less than 50%, we say that it's weak. And then we've got this kind of no man's land in the middle where we have kind of medium strength acids. But there's a whole continuum depending on the chemical structure and the chemical nature of the acid. That's what determines how well the H's fall off. So it has to do with its chemical properties, obviously. Okay, let's do a couple of examples here. Now this example that I'm starting with is actually the more difficult calculation. We're not calculating the percent ionization. We're not just dumping it into the equation, or I would ask you for the percent ionization. What I'm asking you for is the hydronium ion concentration. This is the typical calculation that we do, and that's why I wanted to start with it. I want to just cover a couple of things. Hydronium ion concentration, all right, stands for that. H3O plus reads hydronium ion concentration. So this is, again, the hydronium ion. Now, in your textbook, when you are assigned some problems, even in the grade 12 textbook, they like to talk about the hydrogen ion concentration, H plus, all right? The hydrogen ion concentration is really the same as the hydronium ion concentration. I told you yesterday that a hydrogen H plus will not just sit there and do nothing. It will stick to the nearest water and form an H3O plus. Some textbooks, especially introductory textbooks, think that this is way too complex of a subject for you to understand, so they talk in terms of just the hydrogens. So if it asks you to find the hydrogen ion concentration, that's the same as hydronium. That's the H3O plus. So that's a hydrogen ion. They mean the same thing. All right, that's what I just want to clear up in case you encounter that somewhere else. Now, how are we going to calculate this? We want to find the H3O plus concentration. Now, the reason I'm starting with this one is I want to express to you that this is a really easy calculation and we really don't need an equation to solve it, but I will solve it with the equation. If I have 0.56 molar acetic acid and 1.57% of it ionizes, the question is how much H3O plus am I going to get? And what I'm essentially trying to find is, what's 1.75% of 0.56? This is really a simple percentage math problem, because 1.75% of the H's fell off of this thing. So I can easily get that by expressing my percentage as a decimal, or just dividing it by 100. 1.75 divided by 100, 1.75% of 0.56 molar, and that's going to get me the amount of H3O plus. And I'll take that number when you got it. Yep. It's not a percentage. 9.8, I'd add 2 significant digits is good, times 10 to the minus 3. What is the unit? Yeah, molarity, or moles per liter. Moles per liter. because this was a percent. This is a molarity. Do we like that number? Support on that number? Okay. Let me just show you the other way. If you're a fan of using the equation, you can easily rearrange the equation and solve. Percent ionization is equal to the H3O plus concentration divided by the concentration of the acid times 100. Substituting that in, 1.75, I want the H3O plus concentration divided by the acid is 0.56 times 100. Now at this point, you'll just take this and multiply it, bring it up top, take the 100 and divide it, bring it down below, and I'll bring my calculation up to here. 1.75 multiplied by the 0.56, bringing that up top, dividing it by the 100, bringing that down below, and that leaves you with the H3O plus. And you'll notice it's the same thing, right? 1.75 divided by 100, there it is right there, times 0.56. You get the same thing. So it doesn't matter what version you use here, but it is really just taking 1.75% of the acid concentration. 9.8 times 10 to the minus 3 moles per liter. Okay? Either way, however you get it, doesn't matter to me. Let's do an example of where we're finding the percent. This is actually easier because all we're doing is substituting into the equation and going. Actually, I think, Miranda, you've already got this sheet, right? So I'll just send 4 back there. Don't wait for me on this one. This is just substituting into an equation. You should have a hydronium ion concentration. You should have an acid concentration. And all we're doing is looking for a percentage. Again, the square brackets represent concentration. So we're looking for molar concentrations. Hydronium ion concentration, 0.352 molar. The acid concentration to begin with, 0.50 molar. So we're essentially saying 0.352 moles per liter of the H's fell off successfully. That's what we're saying. Times 100. What do we got for percent ionization? We got it. Jess, you got it? 70.4%. 3 significant digits. Excellent. So that's 70% ionized. All right? Notice it doesn't even say what kind of acid it is. It doesn't matter. We can do a percent ionization and not know the identity of the acid. It doesn't affect anything. All right? Just to finish off, before I let you do that little worksheet, it's just a quick little practice worksheet, I want to talk about how we deal with bases. This deals with what we talked about at the very beginning. We are not going to be using a percentage when dealing with bases. And when dealing with bases, it's the hydroxides we're interested in. Again, all of this hydronium and hydroxides are all going to be encountered in our lesson on pH. So when you deal with bases, it's the hydroxides you're interested in. And in order to keep this simple, because we could be dealing with stuff that doesn't dissolve very well, and oh my goodness, if it doesn't dissolve, then it doesn't dissociate. And that is true, but I don't want you to have to deal with that in this course. In this course, every time you encounter hydroxide, you're going to assume that it is 100% dissociated. All right? That means they all fall apart. We're not even going to worry about whether it's soluble or not soluble. We deal with that in grade 12 as well, how to determine how soluble something is. So this is pretty straightforward. If I've got NaOH and it 100% breaks down to Na plus and OH minus, and I get one OH for each one, then I can write a quick little easy conversion factor, 0.26 molar, and I get one OH minus for each NaOH. We've seen this conversion factor before. It's the one that plucks out ions from a particular substance. If you only get one OH for each NaOH, then you're going to end up with 0.26 molar as being your hydroxide ion concentration, because it's a 1-to-1 ratio. Barium hydroxide, I actually don't even need to write out that dissociation reaction, because just from the formula, I can see that there's two OHs for each barium hydroxide. If I have 0.26 molar barium hydroxide, I'm going to have two OHs for each barium hydroxide, 2-to-1 ratio, and I end up with a concentration of what, 0.52? 52 molar. That is the OH minus concentration. All right? So at this point, I want you to just finish that worksheet that you've got there. It's just a handful of various acids of different percentages. Figure out the hydronium, a couple of bases. I know magnesium hydroxide is on the sheet, and I know I told you it doesn't dissolve very well, but just assume it does. Assume it dissolves 100%, just for the sake of having a different one. And that won't take you very long. We'll take it up in about 10 or 15, and then at the very end, I may start talking about the pH scale. I may get into an introduction so that we have a little extra time tomorrow to practice calculating. Let me just stop this thing 1 second. You got to use the bathroom or something? Okay, I'll get that for you. Let me just stop this thing here for a minute. What am I doing?